We know that magnetic flux is the invisible field coupling electrical energy to mechanical work. But in engineering, a conceptual understanding isn't enough. We need to calculate exactly how much current to pump into a coil to produce a specific amount of mechanical torque on a rotor. This textbook diagram bridges that gap. Figure 1-4a is a standard electrical circuit, and Figure 1-4b is its direct magnetic analog. Just as voltage drives current through electrical resistance, a magnetomotive force, or MMF, drives magnetic flux through a core's reluctance. We can take the standard electrical resistance equation and translate it directly into reluctance, path length divided by permeability times area. And Ohm's law for voltage morphs perfectly into magnetic Ohm's law. MMF equals flux times reluctance. By using these three translated formulas, we can map out and mathematically control the magnetic fields that dictate how every motor, generator, and transformer operates. Let's calculate this on a standard, continuous square steel core wrapped in a 100-turn coil. We know its mean path length, its cross-sectional area, and that this specific steel has a relative permeability of 2000. Our first step is to figure out the core's reluctance. We'll use the reluctance formula, length over permeability times area. Watch out for the permeability trap. That 2000 is only the relative permeability. To get the actual permeability of the material, you must multiply it by the permeability of free space, which is 4 pi times 10 to the negative 7th. Next, before you plug anything in, convert all your dimensions from centimeters or millimeters into standard SI meters. A single misplaced decimal here will ruin the entire calculation. Run those numbers and you get a relatively small value for the core's reluctance. A continuous steel core offers almost no resistance to the flow of the field, giving us highly efficient magnetic flux. Now, let's cut a tiny 2 mm air gap into that solid steel block. By breaking the continuous loop, we've created a series magnetic circuit. The total reluctance of the system is now the sum of the steel core's reluctance plus the new air gap's reluctance. Try calculating the gap's reluctance yourself. Remember, the relative permeability of air is essentially 1, and your gap length must be converted to exactly 0.002 meters. When you calculate it out, the reluctance of that tiny 2 mm gap is massive. It completely dwarfs the reluctance of the entire steel block. Because air lacks the aligned atomic structure of steel, it actively fights the flow of flux. Even a microscopic air gap will dominate the total reluctance of the circuit and dictate the energy requirements of the machine. We add our small core reluctance and our massive gap reluctance together to get the total reluctance for the entire system. Let's say our motor needs exactly 0.05 Webers of flux to operate. We plug that target, along with our total reluctance, into the magnetic Ohm's law. That gives us the total magnetomotive force required. To find the physical current, we divide that MMF by our 100 coil turns. This reveals the exact amperage we need to supply from the wall. This is the complete workflow. You map the physical geometry and material science into reluctance, use the target flux to find your MMF, and divide by the turns to get your current. But calculating the current for a static magnetic field is only the first step. To generate actual voltage, that field needs to move. In the next section, we'll see how changing this flux breathes life into machines through Faraday's law.